Assignment 7.
Yes, sir.
Okay, assignment 7. Good question. Okay, I will share you the screen. Hope you are able to see the screen well.
Yes, sir.
Okay, now tell me your question.
Sir, in the first question,
Hmm.
I have picked the answer because CFD is cheaper than experimental testing, and I think, sir, answer 1A and answer B means because CFD provides more accurate results than experiments because CFD is, sir, A, C, and D. I think three options will be correct in this case, but only one
A, B,
option
and
is
C.
given. Yes, sir. Means according
No,
from my
the
knowledge, I
answer
have
is
seen the.
CFD is used to study wider range of flow conditions than experiment. When evaluating the hypersonic flows, identify the main reason why use of computational fluid dynamics is recommended. Because CFD is cheaper than experimental testing. CFD provides more accurate results than experiment because CFD is easier to set up and execute. See, A, B, C are really not correct.
Why, sir?
CFD is not at all cheaper than experimental testing, especially for computational hypersonic flows.
Okay,
If
answer
you,
C.
I mean, let me give you the complete view. Do you know about the supercomputers in India or supercomputers that use in for computational purpose in any IITs or research facilities?
No, sir, I don't.
Yes, if
Means
you
actually,
are
I
aware
was
of the
thinking about CFD in ANSYS or such kind of softwares. Basically, I don't know
ANSYS
about
also
much
or
deeper.
any open source software also, if you're trying to do anything, it depends on your problem. But for hypersonic flows, especially for telling the hypersonic flows, simple problems like two-dimensional flow problems can be done even for the two-dimensional flows also. It is not at all cheaper. It is highly
Okay.
computationally costly. You need sophisticated computers, especially supercomputers or workstations.
Okay, sir.
Okay, and it's not a cheaper thing. You need sophisticated equipments, but that is not the main idea of why we are using CFD. And the second thing is CFD provides more accurate results than experiments. That's not at all true. Every time when a proper experiment only can give you the realistic results. Even the qualitative results may differ from actual scenario like true jet in the aircraft, and true experimental result may differ in magnitude wise, but actual phenomena flow physics what happening can give you can get in from the experimental results only. So accurate results is not also the criteria, and because CFD is easier to set up and execute. No, CFD is not at all easy to and set up and execute. If you are coming truly from all the basics of governing your their equations and until you set up the equations, it is very difficult to handle the things. It is not at all easy. Anyway, it is again still depends on the what kind of problem you are solving. And the fourth
Okay,
one,
sir.
CFD can be used for the study wider range of flow conditions than experiments. The fourth one is the true answer. It is the only possible way you can say it is a true or the recommended kind of functions. Because in experiments, if you are designing for certain experiments means it should be realistic. So you are bounded to some pipe design. Suppose if you are using a pipe, you have a fixed kind of mass flow rate in that. You cannot increase your pressure if you have a set only one kind of preservation, or if you have a fixed kind of gas, you cannot change your gas. So if you are doing experiments, you are bounded to all these kind of restrictions in the experiments. Hope you can understand now why the answer
Yes,
is
sir.
B.
Okay, sir. Got it.
Okay.
Means
Any
it will be more costlier, I think, in case of setting up different type of flow arrangement in case of wind tunnels because
in
means
case of yes,
flow.
it is. Hmm. Come again. Repeat again. Means.
Sir, wider range of flow conditions can be easily done in CFD than in wind tunnels because in wind tunnels we have to set up the whole instrumentation in that case
Yes,
for different type of
yes,
flow conditions.
yes, yes, yes. Same thing. If you are using a wind tunnel and if you want to set up different velocities, it is very tough job, and you cannot maintain the same turbulence intensity and the flow conditions also. Or different parameters, you cannot maintain it. It will vary in experiments. But CFD is also costlier.
Okay,
You
sir.
should also always keep in mind CFD. If I say per 1 hour, you can count that like in any supercomputer, on average, they will charge around 240 to 500 rupees per a core if you run for 1 hour, one computational cost. So it is like if you it needs to be run for days, sometimes it needs to be run for months. So it will cost you more than 62,000 to 1 lakh and more than that also. Okay.
Okay, sir.
And then
So
second
question number
question you
2.
have. Okay. Which one or more of the following
Sir,
statements about zero?
B and
Yes.
C.
B and C. Which one or more of the following statements about zero lift angle of attack for a thin airfoil is not correct? Which one or more of the following statements about the zero lift angle of attack for a thin airfoil? Zero lift angle of attack means this should be definitely zero lift angle of attack for a thin airfoil. This should be a cambered airfoil, right?
Yes, sir. It is a cambered aircraft.
Should be a cambered airfoil.
Uh,
And the
cambered.
indicated as alpha L equals to 0. Put 0 lift angle of attack for thin airfoil is not correct. They're asking for the not correct. The first one is true. We represent the lift angle of attack is alpha L equals to 0. It is a negative angle. Yes, it is a negative angle. For a positive camber airfoil, it is a negative angle. You know that, right? And
Yes, sir.
it is
But here,
unaffected.
sir, actually here it is not mentioned about the positive camber or negative camber. Actually, I was
It's not
confused
mentioned.
in that case.
You can raise that. You can raise that. But first option A is correct. So that is not your option.
Yes,
You can raise
first
that
option is
query.
correct.
It is a negative angle only for the positive camber, and
Yes, sir.
C, it is unaffected by changing the airfoil camber. So it is the point.
It is a point. Yes, sir. It is
It is the
unaffected
point.
by changing the.
Hmm.
Yes, sir.
So that is
Because
the one, and the fourth,
it will get affected in that case.
it will get affected. So you should check about option B and C. Maybe you can raise the
Yes, sir.
option B if you have ticked it. You should raise the question like it is not a. You did not mention whether it is a cambered or the question. The other did not mention whether it is a cambered, positive camber or negative camber. You can raise it like that.
Okay, sir.
And it is unaffected by changing the airfoil camber. So option is C directly. Okay. Any more questions here?
Question number 4, sir. After this.
Question number 4. Okay.
Yes, sir. How
Which
can
of
this
okay.
option C?
Hmm.
Option C is the means separation point.
Okay.
Sorry, sir. Not option C. Just a second. Favorable point. Yes, option D. Favorable
Hmm.
pressure gradient exists at location 2. Sir, favorable
Okay.
condition will exist only if dpdx is less than 0. But at point 2, it is
Hmm.
separation point. So how can it
Okay.
be favorable pressure gradient for in that case?
Okay. Let me read the question. Which of the following statement or statements about the information of velocity boundary layer in the flow over an airfoil following formation of velocity boundary layer in the flow over an airfoil is incorrect? Okay. Here, xi is the coordinate tangential to the airfoil surface. Where is xi? They did not mention. Okay, xi is the coordinate tangential to the airfoil surface, and y is the coordinate normal to the airfoil surface. Okay. At location 1, uh, dou p by dou x is greater than 0. Location 1, dou p by, where is your location 1? What they're asking is incorrect. Pressure gradient, they did not mention anything. U of x, U of x, U of x is the boundary layer they mentioned. 2 is the separation point, so it is all attached. Dou p by dou x if you see that, yes, dou p by dou x, it's a reducing one. Pressure gradient along the x, if you plot, pressure gradient decreases. Dou p by dou x should be less than 0, right? If you are going along the
Yes,
surface.
sir. Yes, sir.
Okay.
For the
So first one
flow
is incorrect.
conditions for the flow. Yes, sir. First one is incorrect.
Hmm. Hmm. And the second one, zero pressure gradient
Ne-
exists at location 3.
Yes, sir. That is
Zero pressure
also
gradient. That is also, it's a correct one, right?
incorrect. It is zero pressure gradient exists at location 2,
Pressure
I
2.
think.
Okay, yeah, 2, 2, it's 2. Dou p by dou high pressure gradient. Yes, so where the separation point exists, there you have a zero pressure gradient. Yes, it's location 2. And C is there is a favorable pressure gradient in the region 1.
This one
Favorable
is correct,
pressure
sir.
gradient.
Option C is correct.
Okay.
And option D
Favorable
also.
pressure. Favorable pressure gradient. What does exactly they mean the favorable pressure gradient? First one is your incorrect option. Zero pressure gradient exists. And the second one is also your incorrect. Zero pressure gradient exists. There is a favorable pressure gradient in the region 1. What is exactly mean there? Favorable
So
pressure
they are
gradient.
asking for the incorrect ones,
They
basically.
are asking
So
for the
I have,
incorrect one.
yes, sir.
Hmm.
Now I have ticked option A, option B, and option D. So
Okay.
option D also, actually option D I think is incorrect in this case, because favorable pressure gradient exists at location 2. At location 2, it is the separation point where dou p by dou x is equal to 0, is not less than 0. Then how can it be a favorable pressure gradient? Then option D is also included in that case.
Let me see what did they give. A, B that we taught. C, D is the favorable pressure gradient exists at location 2. You opted A, B, and D, right?
Yes, sir. I opted for A, B, and D.
Hmm. Like, what does they mean exactly? What is the favorable pressure gradient? Is it for pressure gradient that gives a
Sir, they are asking flow separation occurring at point 2, and from 3 wave will be formed after 2, means point 2. So they are asking for that only, that where it will be favorable pressure gradient and where will be it is unfavorable.
these C and D options are quite confusing me. The favorable pressure gradient in the region 1. If you see in the region 1, there is a pressure gradient, but what does exactly the word favorable is stating is not clear. There is a pressure gradient in the region 1, and there is definitely you will have a lots of pressure gradient if you can plot the CP plot. Okay,
Yes, sir.
your voice is okay. Now it's okay, your voice. And
Yes.
D favorable pressure gradient exists at location 2. Favorable pressure gradient exists at location 2. Your pressure gradient is going to be 0. That's it at that particular location. So
Yes,
now,
at
why
point
you
2,
are
0.
feeling like it's not a correct answer here? Pressure gradient exists at location 2, right? It's not okay. Pressure gradient exists. It's not discontinuous one. CP is not discontinuous. Yeah, C and D are looking correct for me. Why you are thinking that D is incorrect?
Sir, in the case that wake formation of wake, I think will start because it is a separation point where the flow is starting to separate, just
Okay,
initial separation point. So,
okay,
sir, we know that favorable pressure gradient exists only when dou p by dou x is less than 0. Wherever there is less
okay.
than 0, and after that, if adverse pressure gradient occurs, then it becomes unfavorable pressure gradient. So it is a
So
little bit confusing at point 2, where point 2 is equal to 0. So what in that case, sir, how can we say that favorable or unfavorable?
okay, professor stated that favorable pressure gradient is only for less than 0.
Yes, sir. Dou P by dou X is less than 0, where CP formation will be favorable. CP will be means formed,
Yes, yes.
and after
Okay.
that, wake will be formed. So,
After that, wake will be formed. But this concept of favorable, if you have that stated definition, like anywhere, if you found that in his slides, say that he stated the favorable pressure gradient that dou P by dou X should be less than 0, or you should see the condition less than or equal to 0. If that condition he mentioned anywhere, if it is only less than 0, you please raise the query. I will forward to them. If it is less than or equal to 0, with my opinion, C and D are looking correct. Favorable pressure gradient. If I say in terms of not looking the favorable, if I say only looking at the pressure gradient, then it is okay for me. But if you are saying there is a favorable means the professor stated that dou Cp by dou X should be less than 0. That should be only negative. Then at point 2, the pressure gradient is 0. Then you can raise that option D is also uh, answer for this question. You have that statement anywhere in the slides?
yes, sir.
Because
I have that
I
PPT.
yes, yes. Please note, I mean, note the time of the corresponding video on that and
Okay,
raise
sir.
in accord. You already raised the query?
Yes, sir. I already raised that query.
The same thing what I told now?
Yes, sir.
Let me read the question. I actually don't get the time to completely go through the questions.
No, sir. No, sir.
Let me read your question. Question 4, what is the question number? Question 4, how separation point to have a favorable pressure gradient? Okay, here the question is not complete. In the question 4, how will you raise it? It is once again you raise as a reply to this question, like, dear sir, you mentioned that favorable pressure gradient means dou P by dou X should be less than 0 in this particular video at this particular time. But according to this option, this is not happening. So kindly give us some details about that. Okay.
Okay, sir. Okay, sir.
He raise the query like that, and we will. I will talk to him, or he will respond for your query in the live session also. Or else, if you want that, I will give
Okay,
you in
sir.
the coming session. Okay.
Okay, sir.
Okay. Anything else?
No, sir.
Okay. Okay. Any other queries from anyone regarding the assignments or topic that you are unable to figure it out, or some other details you want?
No, sir.
Okay. Let me see the participants. Danvin, you have any queries?
No, sir.
Thank you, Danvin. So let us start out today's session then. Just give you an overview of the last class. Yes. In the last class, we discussed some of the points related to the airfoil geometry and just a minute. Okay. So we also discussed what is the resultant force on an airfoil and how to handle that, and the moment coefficients and force resolutions from axial direction to the flow direction or perpendicular to flow direction. What is the pressure gradient Cp? So all these concepts you will see continuously in the assignment questions that we just seen in the assignment 6 or 7 also. These are all basics so that you need to remember and you need to apply for the upcoming assignments also. So it will be helpful in that perspective if you revise the classes, whatever we are reviewing here. So we already seen what is the uniform force, source and sink, and their strength, and maybe the doublet and vertex. I hope that you had covered the lectures in video. I mean, maybe in the last week that you had learned about the panel method, and I saw that you there is a good introduction about the things that how these vertex can be used in the panel method, and how the primary flows or the singularities can be applied to model the flow in aerodynamics on an aerofoil or on any lifting surface. And then this is a spinning flow over a cylinder, sorry, flow over a spinning cylinder that can generate the lift, and we call it as the Kutta-Joukowski theorem, a very important, and it's a fundamental in aerodynamics. And then we just seen how we are modeling the lifting of an aerofoil, and then we discussed some concepts of how nozzle works, flow through a nozzle, and these are important concepts when we go for the high speed flows and how to generate the supersonic flows also. The only possible way that we can generate the only possible way that we can generate the supersonic flow is through your nozzle, this convergent divergent nozzle. And yeah, that's up to the last class. And
Sir, can I
yes,
ask a question? Means, it's just from my curiosity point of view.
yes, okay,
Sir, I was looking for that ramjet engine. In case of ramjet engine, this convergent divergent nozzle is being used for
okay,
the formation of oblique shock waves and normal shock waves, and they are means applying this concept in ramjet engines because ramjet engines does not have any moving parts. So
okay.
so basically, sir, how they control this means from last week, sir, you told me regarding this that how area decreases and velocity increases and velocity decreases area and this relation between area and velocity. So
Yes,
in that case also, sir, there is the means they are applying the same concept only.
yes, there is also same concept, uh, similar concept. I don't say the same, but they apply in multiple complex structure. Like exactly what you want to know in the ramjet engine, that velocity formation, or can you tell me what exactly you want to know in the
No,
ramjet?
yes, sir. That velocity formation only.
Okay,
That
so
they are controlling the speeds
hmm,
using the ramjets from the jet engine.
okay,
They are controlling the propulsion. I think
okay,
using this concept only.
yes, there are no moving parts in the ramjet or the scramjet engine, but you need to see that the definition from the ramjet and the scramjet will give you the understanding of how they are controlling the velocity. Suppose if you are taking a ramjet, the flight itself needs to run at supersonic speeds. Let me draw for you. So let us take the simple convergent divergent section, or kind of, assume this is the inlet. So they call it as the lip and the cowl, everything. There are many parts in the ramjet engine, but I am not going to all the details. But the inlets of any ramjet engine, if you see any kind of supersonic flights of a ramjet of the jet engines, they used to have this kind of design at the inlet where air is going to strike the engine. Your aircraft is somewhere like this, somewhere flying at certain altitude, maybe where your density is favorable for you. And then two things need to be controlled. One is you have to, okay, you have to control or you have to reduce the flow speed inside the engine. Suppose if it is your combustion chamber, I'm just drawing a schematical one. If it is your combustion chamber, you have to reduce your speed of the flow, not the aircraft. You have to reduce the speed of the flow that is coming into the jet engine in such a way that it should stay inside this engine for the minimum amount of time that is required for the combustion and proper mixing of the entire combustion fuel in the entire combustion chamber. So to stop that, to reduce its velocity, because your ramjet or the aircraft or the jet aircraft that moves at a supersonic speeds, assume it is moving at a Mach 1.57 or Mach 2, Mach 3, whatever the Mach number it is going at that speed, if the flow is entering into this inlet, it cannot stay for sufficient amount of time, or it cannot breathe. We say it as the breathing of air. It cannot breathe sufficient air because whatever the air is entering, that immediately comes out through the engine. So one should stop, or one should reduce its velocity inside the combustion chamber and allow the fuel to mix entirely by spraying it into a droplets format, and then it should be lightened up with some ignition. Then only the proper mixing can happen. But how you can reduce the velocity as it is going, reduce the velocity of your air as it is going at such high speeds? Whatever they're doing is, since it is coming at a supersonic speeds, two things are happening. One is they are reducing the cross section here. So since they are reducing the cross section means it is nothing but you are reducing its velocity of the fluid. That is what we already learned in the convergent divergent section. But before reducing the cross section, another phenomena that occurs is, since it is already supersonic and you are creating a disturbance due to this lip, there will be a formation of shock waves. Those are oblique shock waves, and these shock waves forms like a train inside the multiple trains it forms. Okay, and these forms multiple oblique shock waves will form inside this an inlet of the jet engine and reduce the velocity of the air entering inside and makes your flow less velocity and able to combust it. So that's how the ramjet works. But if you see the scramjet definition itself is like supersonic combustion, where your flow, let me write it. We say this is a ramjet engine. The first two letters in jet indicates supersonic ramjet engine. Supersonic, this is a combustion here. So in your ramjet, what you're doing is you just uh, combust your fuel by reducing the velocity to subsonic levels using the shock waves and converging area. But in the scramjet, you are maintaining your velocity, or you just decrease your velocity, but still it should be in the supersonic levels. And in the supersonic levels of velocity itself, you are doing the combustion. So it is highly difficult task to do or design these kind of engines, but still research is going on, and some successful engines are also there for few designs are available. So that's why we call it as a supersonic ramjet, or that is a scramjet engine or the ramjet engine. Both you have the technique of using the convergent divergent section. Okay.
Okay, sir. Sir,
Just go to
another
the,
thing
yes,
I want to ask, just
yes,
my last question. Sir, can you just give me some applications of the formation of doublets? Sir, where can we use doublets?
doublets formation that you want to use.
Yes, sir, like the concept of convergent, divergent, and this oblique shock and normal shock I can use in this type of applications. But this formation of doublets, where we use?
That's a nice question. So far, doublets, it's not theoretically or experimentally my practical situation. I never seen, but doublets mostly used with the idea of creating the walls on the surface, or using for the modeling of as a singular points in theoretical aerodynamics. Suppose in the panel method, you have used the vortex for modeling for
Yes, sir.
modeling the flow over an aerofoil on the surface. In the same way,
Yes,
you
sir. In
also
case
use,
of vortex lattice method, I think you are talking about.
yes. In the same way, you also can use source and sink. Professor might have already told you. source and sink
Yes, sir.
singularities that you can also use. A flow over source and sink with a minimum gap between them that you can say doublet. Doublet is also a primary or a singularity that mostly you can see in the theoretical perspective instead of practical perspective, as I say, for the modeling
Okay, sir.
aspects
Okay,
to
sir.
model a flow over and any complex objectives. Like the wall we model with the right now we already always in the model with the vertex and the panel method. Also, you can model with all the singularities, whatever you have available. But the theory will be getting complex and complex if you use other singularities. Practical examples, if I find any sometime, I will let you know. Okay.
Okay, sir.
Okay. And you also remember that vertex is not the vertex that you are seeing in the hurricanes or any spiral that you see in the sink. Sink means the water basin sink, those kind of things. Vertex has a clear definition. Those things, what you are seeing are the spirals, and vertex are available that you can see in the nature, not available. Vertex are common in nature, but all vertex or whatever the shape that you are seeing, those are not at all a true vertex. That can be a spiral also, or that can be just a fluid rotating in a circular pattern. Vertex has a clear definition that it all the fluid particles, whatever that the rotation that you're seeing, should follow the definition that given to the vertex. Okay. So if
Okay,
you
sir.
are seeing something in rotation in the fluid, that does not mean it is clearly vertex. Okay. It will be helpful for you to understand that primary or the singularities, whatever you're seeing, those may not exist all the time. But some singularities you can see on flow over the objects. If you try to understand the singularity of, suppose, a source flow, the flow separation point is a semi singularity, you can say. Separation point is also a singularity where you can see a flow streamline suddenly emerge at that point. It's a new, it stopped from there and it emerged from another point. Like I will give you one more hint to understand it clearly. If you have a flow separation anywhere, suppose you have a flow separation like this, but don't you see any kind of streamlines that exist below this separation line? It is common to see a streamline starting from this point where you don't have any kind of uh, possibilities to generate what do we say, any kind of source or sink. Nothing is there because it is only a wall and fluid is not emerging, and you have a streamline here. That means velocity is passing from this point. So what does it indicates? It is also kind of singularities that we say a source kind of singularity, but it is not a complete source because it emerged from this point in the flow field, and the streamline starts intermittently. It not continuous from the flow. It starts intermittently on this aerofoil because of the flow in the separation region, which is a kind of separation between your potential, not I don't say potential flow. It is from your entire flow field on the top of the airfoil surface and flow in the recirculation region. So these things you can see by deep investigation of flow fields in the real nature, or by using the computational fluid dynamics, or by using experimental techniques. You can see the flow, and if you draw the streamlines or any kind of velocity vectors for that, you can easily identify some parts of these singularities. Not a complete thing, but you can at least identify the singularities. You got it?
Yes, sir.
Okay. And shall we go for the today's session?
Sure, sir.
Okay. So let's move to this session. Yeah. So, good evening, everyone. We are now trying to solve some of the questions that are related to your concepts in your week 4. So, which are also helpful if you try to solve in for the upcoming assignments, as these are all basic concepts and you need to understand or review the things for your future use. So, let's try to solve the questions one by one here. Consider that phi 1, phi 2, and phi 3 represents three distinct solutions for an irrotational. It is always good to mark your key parameters, that is irrotational, incompressible, flow field. If flow field is irrotational and incompressible, yes, which of the following is also a possible solution of that flow field? See, we have two conditions. One is irrotational and incompressible flow field, and these are the five functions for those possible five functions, three distinct solutions for that kind of flow field. So we have four options here, one, two, three, four. So in these four options, we are here to find out what are the possible solutions uh, for this irrotational incompressible. By looking at it, one can easily say the odd things are these two. I just ticked before. I don't know whether you noticed or not. I just ticked um, option A and option D because option B and option C are providing you directly a non-linearities in the solution because you are doing it's also a primary variable and it's also a primary parameter and you are doing the multiplication of these things and you are doing operation of non increasing the possibilities of non-linearity, and in the same way uh, in the option C also you are doing the same thing. It's a common or immediate response that you need to get once you see the question, but it is not the complete picture of the question. It is just a basic idea for your competitive kind of exam to answer these kind of question immediately, where if you are having a solution or possibility governing equation for these irrotational incompressible flow field, we have the governing equation for these two conditions is Laplace equation, that is del square pi. The del square pi is a linear potential equation. Because it is rotational and incompressible, you don't get any kind of non-linearities or you don't see any perturbation kind of things. So it is a linear uh, potential Laplace equation. For these kind of linear governing equations, if you have, even though if you add some term for your answer, if you are adding some term that is of the same kind of parameter, you don't get any kind of difference or you don't get any kind of variance in your solution for if you add these kind of terms to your primary variables. So that is why the first option is correct, even though you're adding pi 1, pi 2 plus pi 3, because those are also solutions for your system. And since you're adding these terms, then it won't give you any kind of problem and it will be also act as a solution. But if you are doing this kind of nonlinear parameters that multiplying that gives increase the nonlinearities, this won't give you the correct solution. For your better understanding, I will just show you some simple differential equation function. Suppose if you have an d by dx, and so I will say go by, let me erase it. Dou by dou x of suppose 2x. Okay, 2x square. I'm just saying dou by dou x of 2x square. And if you use this, this can be multiplied with some constant, and this can be added with some constant. Okay, or if you say this wants to be some particular function of your system, this can also, like if you are using any additional term, dou x square times again x, this will modify your solution. It cannot be satisfied. I will say equals to 0. This will become dou by dou x of 2x cube just for your understanding, not for the actual scenario. And it's a 2 and 3 times x square. I will say this is some constant. Instead of 0, let's take it some constant. So 2 times 3 and it is x square. So 6x square you will get as a constant. Okay. Now, if you are dealing with some you're dealing with some multiplication. So as you are adding, uh, sorry, if you are adding the parameter like this to the solution, that is same as constant. And if say if you are adding like constant c1 or multiplying with the constant c1, and this is your function, this can also be possible, right? D by dx of x, you can split it, and dc1 by dx, this will go up to 0, and your function dou by dou x is same as your function. So adding a constant or multiplying with a constant and giving up the same solution, better solution approximation you can get from e power x. Um, you can see the general solution for any differential kind of equations is commonly involved with the e power x when you have learned the solutions for the partial differential equations or linear differential equations. There it is a common property uh, that involves all the solutions with the e power x, which has a capability or which has a function like it generates the same realistic value again once you differentiate with the, or once you do the partial differentiation or the actual differentiation with the sorry, dou by dou x or whatever differentiation you are doing. So keeping in the same mind, you have the possibility of getting the same answer by adding up the solution or by adding a constants to this solution, some arbitrary constants. But if you're multiplying or division that, then it will give you a unrealistic kind of answer. Okay, so let's go to the next question. The second question, consider an airfoil body surface. We have that airfoil body surface to be a streamline of an inviscid flow. Well, bodies consider an airfoil body surface to be a streamline of inviscid flow. Okay, which of the following is or are the boundary condition or conditions for the velocity at the wall? We have a airfoil body surface, and they are asking us to identify what are the boundary conditions that are necessary to be the streamline is acting as necessary condition to state the streamline that can act as a wall. One thing is if you are working on any streamline or if you are making the things acting as a wall, whether you should be clear you are dealing with the tangential velocity and the normal velocity. For the primary thing, whether it is a potential flow or the viscous flow, you should have your normal velocity, that is Vn, should be equals to 0. Okay. For our Vn, we have two kind of non-dimensional, sorry, dimensionalized kind of parameters to get the velocity values by using the potential functions and the stream functions. If I want to get the velocity normal to my surface, this is my surface, suppose this is my surface. And if I want to get velocity that is normal to the surface at this point, I can use my potential function where dou pi by dou n. Dou n indicates the direction normal to the surface. If this dou pi by dou n, if you do the partial derivative of the pi with n, then you will get velocity normal to the surface. Since fluid cannot enter through the surface, the velocity that allowing the fluid on into the surface should be equals to 0. That means dou phi by dou n should be equals to 0. So your first answer is the necessary. First, there are many statements here. So whatever the first statement given to you is required condition because your dou pi by dou n is your required condition and it is necessary, that we just seen why it is necessary. It's a unit normal vector to the airfoil surface. And the second one is dou phi by dou x, dou s is equals to 0, where s is the distance measured along the aerofoil surface. we just seen how to get the normal velocity using this potential function. But if we have only the stream function, how we will get the normal velocity? If you want to get the normal velocity using the stream function, you have to do with a component of space parameter that is parallel to that wall. Suppose if this is my wall, I have to take a small distance that is tangential. This is the S direction, S cap. At this point, I have to take a small distance that is ds. I have to differentiate that stream function with a small distance that is tangential at that point. So if I do that, I will get the normal velocity, that is velocity normal to that surface at that point. Okay, so if you are getting this normal velocity and you have to state this also should be zero because the fluid again cannot enter through the surface, right? That's why you are stating that Vn also as a zero. So the second statement is also a necessary condition. Arhit, I just want to ask you that have you ever seen the questions that are repeating whatever I was telling? That you have you also seen in your assignments in the current whatever assignments you are doing in your all the weeks?
Yes, sir.
Some questions are repeating.
Yes, sir. This question has been repeated, sir.
Okay, this question is also is repeated one.
Yes, sir. Sir, mainly, sir, I have solved this question. This question has been given from that J.D. Anderson book. So I was
Okay,
studying that book and I have solved this answer from that only. So
okay.
this question is repeated question, sir.
This question is a repeated question. So in your present assignment also, this question is there.
No present assignment, no, sir. Past assignment there was.
No,
Not
no, no.
present
Past
assignment.
assignments. Yes, past week assignments.
Yes, sir. Yes, sir. Past week
Okay, in
assignments.
the past
This
week
question was
assignments.
there.
Okay. So let me know if sometimes the questions are repeating. Okay, if whether it is past question, then it is fine, not an issue. We don't need to worry about it. But if the future assignment questions, I should not repeat it. I have some kind of questions with me, and I cannot repeat. I mean, I reveal those questions unless you complete the assignments. Okay. So if it is already done, then there is no issue. Anyway, I am also not taking the questions from the upcoming weeks, so you don't need to bother about it, whether it is repeating or not repeating. Okay. And we have a third condition that is V equals to 0 and no slip conditions. We don't need to all acting as a condition. We are not bothering here. It is whether it is stating um, viscous flow or inviscid flow. So if it is viscous flow, the magnitude of V should be 0 at this point. If it is not the viscous flow, sorry, the statement is clearly given here. It is an inviscid flow. I forgot to mark this time. It should be an inviscid flow, so you no need to worry about that. V equals to 0. So it's not a required condition. But at the option D, if you see, you have dou V, dou Y by dou X equals to V by U. It is a clear definition of a streamline. From the definition of a streamline, if you do the cross product del dot V bar, that will give you a ds, and then uh, del, sorry, this is not a del cross V. From the definition of the streamline, you have ds cross V bar. From that, we are doing also finding the determinant of this ds cross V bar, you will get dou y by dou x equals to V by U. Okay, so from this, it is a clear definition of a streamline. And what the question is also saying that the airfoil body surface to be a streamline in inviscid flow. So that's why we need this final option also. So these are all A, B, and D are the required options in this question. Okay, let us go to the next question. In this question, we have a source with a volume rate of point. Just give me a minute. Am I audible?
So, hello, sir.
Yes, sir.
Am I audible?
Yes, sir, you are audible. Sir, your voice is a bit means lesser.
Hello? Hello?
Yes, sir.
Uh,
Sir, you are not. means Voice is very slow, sir.
Hello?
Yes,
Am
sir.
I
Now you
audible?
are
Great.
audible.
Yes, yes, yes. Sorry for the
Yes, yes,
interruption.
sir.
Okay. Sorry for the interruption. Okay. Now let's see the question number 3. In this question number 3, we have that a source flow with a volume flow rate of 0.72 meter square per second and per unit length. Clearly mentioned that it's a volume flow rate and the units are like 0.72 meter square per second per unit length. So the clear units are meter cube per second and is placed per unit length. And it's not per meter square. It's units of 0.72 meters per second, meter square per second only. Don't worry about this. And is placed at a location at minus 1.5 comma 0. And the sink is also there with a volume flow rate of 1.44 meter square per second. This is also per unit length only and is located at 3 comma 0. Let's take a origin and we can clearly understand what we are going to do. So here we have a source with a volume flow rate. Source is kept here at minus 1.5 comma 0. The sink with volume flow rate at location 3, that is twice the distance of it, 3 comma 0. Here you have a source, here are the sinks. Determine the dynamic pressure at 1.5 comma 1 at a location somewhere here. They are asking at this point we need to find the dynamic pressure. Assume the dynamic pressure at the origin. The dynamic pressure at origin is given as 15 kg per meter second square. So we need to find out the dynamic pressure at this location, and we have the dynamic pressure at origin, and we also having the source and sink flow. To understand this question completely, one needs to clearly place the source and sink flow on a graph like this. Suppose if you have an x coordinate and y coordinate, and then we need to find out what is the influence of source and sink on this point by just drawing. Let me draw the distance from this point to this point is some vector or some distance, a magnitude. We need to cross all this x distance and y distance. And since we are dealing mostly with the polar coordinates, let's use the same polar coordinates here. This is the distance r1 and we are having from that source theta is theta1. And then since it's a point, some point that I drawn in a realistic way. And again, this is your point and this is your theta2. They asked for the point at 1.5 comma 1. Yes, x equals to 1.5 and 1. And this is your source flow. And this is your sink flow, right? And yes, that's all. Now, if you individually have the source flow, you can write the stream function of the source flow and you can find out the velocity at that point by using the radial derivative or dou by dou r, dou by dou theta, sorry, dou by dou dt of the stream function, and you can find the velocity at that point. And if you have the density value, also you can find the dynamic pressure. But now you are having the combination of source and sink at different locations, and you are finding out the dynamic. You need to find out the dynamic pressure at some height location. So what we need to do is we have to add up the stream functions of these singularities to find the combined effect of these singularities and to find the dynamic pressure or the velocities that induced by these source and sink flow at different points in the entire domain that we are concentrating on. Suppose if he is the domain that we are concentrating on, we need to first individually see the effects of um, source and effects of sink, and we have to add up the delete or subtract the velocities that is corresponding to. So as we are doing the addition or subtracting, let's go directly first seeing the stream function value from our theory classes. The stream function is not the value. We are just, let's see the directly its function. The stream function psi equals to the volume flow rate by 2 pi theta, and it is plus for the source flow. Okay, pi source flow, it is plus volume flow rate by 2 pi theta, where theta is your angular location. Okay, so there is no value of r that we included here. We only are bothering about the theta. Okay, that will give you your stream function. And then the same thing for the sink flow. If you have psi, the volume flow rate by 2 pi theta, but you have the negative value. So combinedly we can write it as plus or minus 2 pi into theta. So whether it is source flow or sink flow, you can write like that. But since our theta is not same for source and sink, because theta is theta 1 and theta 2 for source and sink with respect to the point P where we need to calculate the dynamic pressure, we need to write separately that psi equals to lambda by 2 pi theta 1 plus of minus lambda by 2 pi theta 2. We need to add the stream functions of both to get actual velocity field. Okay, once you've done that, what you can do, you can take out the common parameters, that is psi equals to lambda by 2 pi times theta 1 minus theta 2, right? If you are doing with theta 1 minus theta 2, what is the, sorry, here is a one more problem is your volume flow rate is not common for the both source and sink. See, if your volume flow rate is common, the value is constant for your source and sink, you can take out this uh, capital gamma, sorry, like capital lambda, and you can take out this and you can simplify like this. But here your volume flow rate is not constant and it is lambda 1 and lambda 2, so I will write it as a lambda 1 and lambda 2 here. Okay. Next, let's substitute the values, but before substituting the values, we also interested to see how we can write this theta 1 and theta 2 in terms of known functions. Like suppose if I want to write the theta 1, I can write it as like tan inverse of y by some distance, that is y by x. Let me write it as a y by x. But if you want to write the y by x, the x is not from the origin. You have just shifted the x to this position, that is minus 1.5. Okay, or else the actual definition is like tan inverse of y minus y1 by x minus x1. You can write any theta if you have a shift in origin, or if you want to take from this position, you can minus those values and you can write these things. Okay, now I want to write my theta 1 in this term. So my theta 1 equals to theta 1 of tan inverse of, I don't want to shift my y from the origin, so I will, sorry. So I don't want to shift my origin, so I will use the same thing. So my y1 is 0 by, I want to shift my x by minus 1.5 as since I placed my origin at minus 1.5 distance from the x, so it will be minus 1.5. So one can write your theta 1 equals to tan inverse of y by x plus 1.5. Okay. In the same way, if you also write the tan theta 2 as we just wrote for theta 1, theta 2 equals to tan inverse of y by x minus 3 because we are shifting our origin to 3 units to the right side of x. Okay, right side of the origin. So this will be your theta 1 and theta 2 function. So let's substitute that. Then psi equals to lambda 1 by cap 2 pi by uh, tan inverse of, for our theta 1 it is y by x plus 1.5, right? And then you have minus lambda 2 by 2 pi times tan inverse of y by x minus 3. Earlier we also seen that to find out the velocity at that point, we need to find the corresponding velocities like radial velocity and the tangential velocity. But because we started first with the polar coordinates, that is theta 1 and theta 2, where r also includes here, that is the radial coordinate, but we just shifted to Cartesian coordinates by using this tan function, that again we have here only y and x functions. So now it is good to take Cartesian coordinates, but if you are individually handling the source and sink flow, you are you prefer to take the radial coordinates and the tangential coordinates like this to find out the radial velocity or tangential velocity. But now my equation includes only the Cartesian components, that is x and y. I prefer to take u component and v component by partial differentiating the psi function with x. If I do dou psi by dou x, I will get a minus v component at that position, whatever the value that I want to include in x and y values. Suppose we have given the we have the value of a point at minus, or sorry, 1.5 and 1. So if I substitute these values in this, once I do the partial differentiation, then I will get the velocity of v at that point. So let's do the partial differentiation for this. Dou by dou x of lambda 1 by 2 pi. You have the lambda 1 value as a constant, so I can take it out. But let me write the equation first. X plus 1.5. Okay. Then it will give you, I will just write the first equation. Then we can also do by partial difference dou by dou x of second equation also. Then we have to add up both. Or it is better to not confuse you. I will write both at a time. Dou by dou x of minus lambda 2 by 2 pi tan inverse of y by x minus 3. We have a differential equation that d by dx of tan inverse of x is equals to 1 by 1 plus x square. This is the standard differentiation equation that you can use here. And if you apply the same in this, we will get, we are doing with dou phi by dou x, right? We will get the following equation. I'm not simplifying. It's you can just substitute those simplification and you can do the simplification. And then you will get v equals to, where lambda by, it's your first lambda, that is lambda 1 by 2 pi y by x plus 1.5 whole square plus y square minus 1.44 by 2 pi times y by x minus 3 whole square plus y square, right? This is the equation you will get for your, it's a kind of looking a complex, this 1.44, since I did not submit the values of lambda yet, I will write it as still lambda 1 and lambda 2. This one still refers your sink flow and this one is referring your source flow. That is your V velocity component. If you are looking for, we need absolute velocity at the point P, not the velocity V component. Velocity V component refers a velocity in the y direction, but we need a true absolute velocity at that point, so that we also need a u component, that is velocity in the x direction at that point. Sorry, I will take one more slide. Give me a minute. Where we are. Here. So if you want to do calculate dou psi by dou y, you will get the u component, and for that you also need again the same equation to be differentiated with the y, that is lambda 1 by 2 pi, and then tan inverse of y by x plus 1.5, okay, minus dou by dou y of lambda 2 by 2 pi, and then tan inverse of y by x minus 3. This is 1.5. Okay, so if we simplify this, what we will get? We will get the u equation like follows, that is lambda 1 by 2 pi times x plus 1.5 by x plus 1.5 whole square plus y square minus 1.44. This is again, let's not substitute this yet. This is lambda 2 by 2 pi, and then x minus 3 over x minus 3 whole square plus y square. Okay, this is your u velocity component. Now, since you have a u velocity and y velocity, you can, equation point of view, algebraically we have, if we want to calculate its numerical value, let's substitute the points like the given point P at x equals to 1.5 and y equals to 1. Let me see whether it's correct or not. Yes, the dynamic pressure they asked to calculate at point 1.5 and 1. Why we are calculating the calculating this u and v velocity components for calculating the dynamic pressure, since the dynamic pressure is given like this. Dynamic pressure indicated by the letter Q, and its equation is half times rho times v square. If you are having a velocity, you can find out the velocity, but how we can find out the density? We just already found the u and v components. We just need to substitute its values, but we don't have the idea of how to calculate the density. That we can see in a few seconds, like how to calculate this density with the additional information given. So let me use this velocity components to substitute in the u and v velocity. If you substitute the coordinates, that is x equals to 1.5 and y equals to 1, then you will get the u velocity equals to, also note that the lambda 1, that is for the source flow, you have what is the value for it? It has a value of 0.72 meter square per second per unit length. It is not correct to write like meter square per second per unit length. It is not the exact thing. It is meter cube per second per unit length. Meters cube per second per unit length. Then if you, this is per unit length, then if you do that by meter, then it will become meter square per second. So that is what a slight correction needed in the question. And the same for the sink flow, the value is 1.44 meters square per second. I will write directly instead of using per unit length. So now I will substitute all these values in the U equation. If you substitute just as a numerics, I request you to play with this uh, by writing by yourself. If you do that, you will get U equals to 0.72 by 2 pi times x equals to 1.5 plus 1.5, and again here 1.5 plus 1.5 whole square plus y equals to 1 square minus lambda 2. Remember that sign convention we already used for the lambda 2, so no need to use it again. The common mistake that we generally do. So 1.5 minus 3 by 1.5 minus 3 whole square plus y equals to 1. Okay, then if you solve for the u, you will get 1.44 by 3 pi, or you will get 0.15 meters per second. This is your u component of your absolute velocity. Okay, if you do the same for substituting all these values in the v velocity, you will get v component equals to 0 meters per second. I request you to just substitute all the given values here in the u equation algebraic form that we seen in the previous slide. If you substitute that, then you will get v equals to 0 meters per second. Now we got the u and v components, that is v bar equals to 0.15 I cap plus 0 j cap meters per second. Then absolute of v is equals to 0.15 meter per second. Okay, so this is our absolute value. We got the v. If we can square it, we will get the 0.15 square. But how can we find that dynamic pressure? Sorry, how can we find that density of the fluid? We already have the additional information that velocity or dynamic pressure at origin is 15 kg per meter second square. Kg per meter second square. This is what the value we have for, that is also half rho v square. This velocity is corresponding to velocity at your origin. Okay, since your density is not a variable here, your variable is only your velocity here, and your dynamic pressure, as we are not changing anything, we have the dynamic pressure equals to let me hold it for a second. What here I did, okay, yes, this is the correct. So to find this density, we also need the additional velocity parameter that is at origin. Let me go to the previous slide. If you see, you have the dynamic pressure here. Sorry. If you have the dynamic pressure here, half rho v square, this dynamic pressure is Q, that is Q naught, I will say, that is corresponding to dynamic pressure at origin, that requires the velocity at the origin. If you substitute the velocity at the origin, then only you will get the dynamic pressure value at this location. But we already given the dynamic pressure value at this location, and we already have the velocity functions, that how velocity is going to vary and the entire flow field with respect to the coordinates. We already have this, so we need to substitute those values of velocity, not the one we calculated just for the point P. So we need to find out the velocity at this point also, and then we can find out our density. So one more task we need to do is we need to find out the velocity at uh, the origin. I will just write the equations of u and v once again for you. and then we can substitute the u equals to values of x and y as 0, then we can get the velocity at that function. Let me write the equation of velocity, that is u equals to, we obtained it by doing dou psi by dou y, that will give you 0.72 by 2 pi times x plus 1.5 over x plus 1.5 whole square plus y square. Fine. Minus 1.44 by 2 pi times y over x minus 3 whole square plus y square. Right. Is it correct? No, sorry. This is wrong. So this will be x minus 3 by x minus 3 whole square plus y square. This is your u value or u function, and your v function is, you can obtain by dou psi by dou x, that is 0.72 by 2 pi times y over x plus 1.5 whole square plus y square minus 1.44 by 2 pi y over x minus 3 whole square plus y square. This is your u and v functions. Now we need to get the velocity at origin, that is x equals to 0 and y equals to 0. If you just substitute the x equals to 0 and y equals to 0 at these points, okay, okay. A minute, I think. Okay, sorry. If you substitute x equals to 0 and y equals to 0, I think it is better to do it numerically here. I, by mistake, told these two equations as I did not solve directly here. Here we got some values, right? That is, where are these? Yes, these two are not the exact values. These values are, this is not 0. These values are, yes, these values are 0.14 meters per second, and this value is minus 0.06 meters per second. These are the numerics. We did the process as correct, but the numerics, as we did not calculate here, that I wrote by mistake the different values that is corresponding to other coordinates. But if you substitute the coordinates of x equals to minus x equals to 1.5 and y equals to 1, these are your actual velocities, and your velocity vector is like this: v bar equals to 0.14 I cap plus minus 0.06 j cap. Sorry for that. And if you do the same process, that if you substitute x equals to 0 and y equals to 0, here you will get, I just substituted those values in the reverse, but here you will get u equals to 0.15 meters per second and v equals to 0 meters per second. Okay, so since this is the velocity at origin, your velocity vector is like this: 0.15 I cap plus 0 j cap, and your modulus of velocity is 0.15, and you have the dynamic pressure at this point is 15 kg per meter second square, is equals to half density times modulus of v square, that is 0.15 square. Okay, now calculate the density from this. If you calculate the density from this, rho equal, you will get 1333.34 kg per meter cube. This is the density value that you will get. And we already have the velocity from the previous, like we just at the last step, we need to calculate the dynamic pressure at this point, and we already have the velocity at this point. We just got that is velocity v bar equals 0.14 I cap and minus 0.06 j cap. So this is the velocity we get. With this two, as we already have density, we can get the dynamic pressure, that is q at point A equals to half times density 133.34 times of v square. The velocity is what are the velocity values? The velocity values is the modulus of this one, that is square root of 0.14 square plus minus 0.06 square. Okay, if you cancel that, you will get the actual value. To simplify this, you will get the velocity dynamic pressure at Q at point A as 15.48 kg per meter second square. So these are the steps involved in this solution to find out the dynamic pressure at this point. But in general common problems of source and sink flow combinations, we either try to look for the stream function or the potential function, or in the problem itself, you will get either velocity functions or any derivatives of potential functions or the stream function. You should appropriately choose the correct thing. Suppose, since in this question, I will just show you the question again. Since in this question, we have the source and sink flow and ask for the finding the dynamic pressure at this some point, we can use the stream function as well as the potential function phi also in this question, because the potential function phi also can be solved by, but there you need to substitute the logarithmic, the function. If you see the potential function that involves is a function of some r, that is a logarithmic r, some function of r and for the source and sink flow. You can recollect from your classes. Either you can use your stream function or your potential function and follow up the same process. But the potential function also has the simple definition like dou phi by dou r is equals to your VR, or in the same way dou phi by dou x equals to your Vx. So you can follow up the same function and you will end up at the same solution, that is the dynamic pressure. So it is up to the user or the mathematical convenient, whichever will give you the fastest and easiest solution. You can try. Okay, fine. So any questions so far? Okay, if no questions, we can proceed for the next question. In this question, the author is asking, saying that a source of strength lambda and a sink of strength minus lambda are located at minus b comma 0 and b comma 0. Let me plot the graph again. Source and sink of same strength are placed at minus b comma 0. This is your source. And this is your sink minus lambda at b comma 0. Fine, right. These two source and sink flows are at a distance of minus b comma 0 along the x-axis with a uniform flow field velocity. You have a uniform flow field here. That is with the velocity v infinity. Moving along the positive x direction interacts with the above singularities. Determine the equation of the stagnation streamline for the resulting potential flow field. All we are taking is the singularities, and it will create only the potential flow field. And then the question is, find out the streamline that is uh, passing through stagnation points. Since you have a source flow here, it from here source flow, you will get the emerging fluid in the left, I mean, in all the directions the same way. And in the same way, you will get all the incoming or diverging flow field diverging towards the sink at this sink flow. You will see from your theory, we already know that there is a formation of Rankine oval. Okay, so the formation of Rankine oval, we already learned from the theory classes. Now our question is find out the streamline of it. Streamline function that corresponding to this kind of flow field. How we can find it? We can find again by taking some point in the flow field, and we need to derive the stream function that comes, generalized stream function that comes for any point in the flow field. And then we have to set up the conditions like at this point, that is point 1, we know the angular location of this point and angular location of these 2 points, point 1 and point 2, stating that stagnation point where the velocity is going to be 0. And we have to, since we are applying these 2 conditions to the streamline function, and we will get a particular function that where your streamline is passing through all these 2 stagnation points, and that is what they are asking as a stagnation streamline resulting by this flow field. So how we can do that? Let's take again the same way that this is the same approach that we seen already in the previous class. Let's take a point in the flow field at some location that is point P, and let's draw the 2 lines and with the sign convention θ1 and θ2. And if you apply the same, and your stream function will be like stream function psi equals to, you will have I think u infinity x for the u infinity into y for the uniform flow field. That here it is the stated, it is a v infinity, not the u infinity. So it is your v infinity y, okay, plus capital lambda by 2 pi θ1 for the source flow, minus represent for the sink flow 2 pi θ2, right? You should see that if you want to work with some equation, it is always recommended to use a particular form of coordinates. Since the source and sink flow are already in the polar coordinates, let's transform that y also to the polar coordinates. That is how I can transform. If I'm taking some point in the flow field, and this is my x, and this is my y, and this point location in the flow field, I can write this, it is your r, this is, and this is your theta. I can write this is a r sine theta, and this is my r cos theta. So since I have that is y value, this is your x value. Since I have y here, I will write stream function psi equals to a infinity times r sine theta plus capital gamma by 2 pi θ1 minus capital gamma by 2 pi θ2. Okay. One more thing. Here, the stream function they asked is to find out for the stagnation points at that is passing through the stagnation point. We know that stream function psi is a constant numerical value. Let's say it's for the, let's write it is just a constant. And then how we can determine this constant, because for a particular streamline in the flow field, the psi value is constant. So that's why we are trying to find that particular streamline, and we are stating this equation as a constant. This is our first criteria to find out the particular streamline in the flow field by stating the equation of the streamline as a constant. If you are generalizing the equations of the streamline in the flow field, you cannot state it as a constant because the equation's psi values changes if you change your streamline. But in our condition, we want to find out only one particular streamline, so I'm stating it as a constant. So our first condition is done, and two more conditions we have. That is, for this Rankine oval, we can see from the theory that there are two possibilities of stagnation points. One is at theta 1 equals to pi and r equals to, we don't know the r values here, but theta 1 equals to and theta equals to theta 2 equals to, that is corresponding to this point. I'm saying if your theta 1 and theta 2 and your theta that is corresponding to your location from the origin, I will say from, I'm saying from this is from the origin, I will say that is theta. So all these equals to, if those all these things equals to, that is corresponding to this location, that is all theta 1, theta 1, theta and theta 1, theta 2 equals to pi for this first stagnation point. So if you substitute these values, okay, you will get one kind of constant, okay, and also you will have another thing, that is the stagnation point corresponding to this point, that is at point 2. You will have theta 1 equals to theta is equals to theta 2 equals to 0. Okay, if you substitute both the things, just substitute directly that theta 1 and theta 2, you will get this second, from the second point you will get, I will just show you how you will get, that is psi equals to, I will substitute the first condition, sorry, this is the second condition because the first condition is already a constant that you are applied it, and this is your condition 2 and this is your condition 3. If I apply my first condition, sorry, second condition, v infinity r sine of pi, that means this part is 0, and then plus lambda by 2 pi, the theta 1 is your value pi, okay, minus lambda by 2 pi, and your theta 2 is also pi, and your value is constant. If you just we already substituted that sine pi is 0 for us, so this value is 0, plus lambda by 2 pi, pi get cancelled up, and minus lambda by 2 pi, again pi get cancelled up, so you will end up that constant equals to 0. Now you have another condition, that is theta 1 equals to theta equals to theta 2 equals to 0. You substitute the same, these theta values in this, you will again end up with the constant equals to 0 for condition 3. So in all these conditions, 2 and 3 conditions, we are getting the same stream function. That means it is only possible 2 points having the same streamline and that constant is 0, then that is corresponding to your stagnation streamline passing through these two stagnation points. That is what they asked. That is psi equals to v infinity r sine theta plus lambda by 2 pi. I took the lambda as a constant common because since the source and sink flow are having the same strength, and then theta 1 minus theta 2 is equals to 0. This is my required function for the streamline that is passing through stagnation points. Okay, I hope it is clear for you. Okay, it is also necessary to understand that no flow, the uniform flow that is coming from this free stream cannot pass through this Rankine oval. It acts as a wall in this flow field. You can have a tangential velocity at every point, but you cannot have the normal velocity because streamline itself has a definition of that. There is no streamline we can draw only a tangential to the velocity vector. It cannot be drawn normal. So there will be no normal flow in this flow field. So whatever the fluid contains or whatever the particles contains in this oval will stay in this oval and it will not come out or pass through this wall. So it acts as a solid body or a solid Rankine oval in the flow field of uniform flow field. Okay, this is a beautiful dynamics that you can see from from this theoretical analysis that physically how you can model a wall in the mathematical how you can model a wall in the flow field without realistically placing any walls or any kind of components. Okay, with using a simple flow physics. So any doubts?
No, sir.
Okay, thank you. If no doubts, we can proceed for the one or two more questions for today's session. So let's see the next question. It's a question asking us to state whether the following statements are true or false, or what is the factness of the statement. Let's read the first question. We have center of pressure is a point where resultant of distributed load effectively acts on the aerofoil. This is our statement 1. And statement 2 is center of pressure is a point. I think this call is recording. Yes, this call is recording. And the center of pressure is a point on the aerofoil about which the pitching moment is exactly 1. Okay. Center of pressure, pitching moment. The true definition of the center of pressure is from its meaning. Let's try to understand. I hope you already know the actual meaning of the center of pressure, but
Yes, sir.
yes. So let me show you how the center of pressure is actually defined. If you have an aerofoil like this, and if you are trying to calculate the distributed load because of the distributed pressure, since your pressure is varying along your surface, we already seen the pressure gradient plot, and the load distributes along the surface because of your distributed pressure. And if you integrate at every point your pressure, then you will get a small velocity or sorry, small force component at that particular location. What we need to do is we need to integrate all those velocities on the entire surface, or we need to sum up. Once we sum up all these forces, we will get the resultant force. The location where this resultant force acts is called your center of pressure. That is XCP. That is only the true definition of it. So the answer is statement 1 is true and statement 2 is false. We don't have a definition of the pitching moment. It should be exactly 1. It can be 1 based upon certain conditions, but it cannot be 1 at all the conditions. And the second thing, okay, let's go for the next question. That is, we have in a low speed incompressible flow, the following experimental data are obtained for an aerofoil section at an angle of attack 6 degrees, that is CL equals to 0.9 and CMC by 4 equals to 0.1. What will be the location of the center of pressure? If you want to understand the mathematically, two things, one more important thing at the center of pressure is, I will show you that the diagram. Since your resultant force is acting at this point, your movement, the clockwise or anti-clockwise movement at this point is equals to 0. Okay, so where the movements are equals to 0, there your resultant force acts. So that's point we say it as a XCP or the center of pressure. Using that definition, we need to find out the answer for this question number 6. What is the question is, we have the given data of CL equals to 0.9 and CMC by 4 equals to minus 0.1, right? And the given angle of attack alpha equals to 6 degrees for this particular question. And whether we need to use it or not, that we can see it later. From the question, we can, given data, we can calculate that moment about the leading edge for this case. You know that the CL lift coefficient that one can place at any point along the chord. Okay, so I'm now drawing my aerofoil like this, say some angle of attack, and I will calculate the moment at the leading edge. Okay. And then if I calculate the moment about, if I want to calculate the moment about leading edge, that is equals to moment about the quarter chord point MC by 4 plus the distance, that is lift force time, that is a quarter chord point, that is C by 4. This will give you the moment about the leading edge, but whatever we have, it is all in non-dimensional format. So if I want to do the non-dimensional, what I need to do is I need to do fraction it by Q infinity into S, which is the dynamic pressure times surface area. Since it is a moment, I need C also. So if I multiply this, I will get a non-dimensional form that we already discussed in the class. I will just write this. You will get the non-dimensional form like here I did not write the non-dimensional form. Okay, let us non-dimensionalize it. But before non-dimensionalizing it, why we are writing the moment about leading edge is, once you get the moment about leading edge, you can write directly that moment about the center of pressure XCP plus lift coefficient times the location of XCP. You see, now your MCP is 0 for this case, okay? Because as our definition, the moment about the center of pressure is 0, right? Then I can equate these two equations, equation 1 and equation 2. If I equate these two, what I will get is MC by 4 plus L cross C by 4 is equals to L times it is XCCP. It is a dimensional one. Let's remember that all the time. And then if I divide it by lift on the both sides, I will get XC by 4 is XCP is C by 4 plus MC by 4 by L. Okay, MC by 4 by L. This is what we have. Now let's divide it by using a non-dimensional format. That is XC by C is equals to, like, whatever the XC by C by value I want to here, I want to non-dimensionalize it. If I want to non-dimensionalize it, I just need to multiply, so divide it by C is equals to C by 4 into 1 by C plus MC by 4. I can write it as like this, MC by 4 and by Q infinity SC, or just Q infinity into S by L by Q infinity into S. And then we need to multiply one more term, that is 1 by C. Once you do that, once you simplify this algebra, you will get that it's all simple algebra. If you turn because it is Q by Q infinity is, I multiplying Q infinity, dividing Q infinity is on the numerator also, on the denominator also, so you can write like that. And I'm multiplying 1 by C on the both left and right. So if I simplify this algebra, what I will get, the non-dimensionalized, say X bar CP, it's a non-dimensional form that prime indicates, is equals to 1 by 4 minus coefficient Cm C by 4, the coefficient of movement at quarter chord point, as you have this one, this all is the coefficient of movement at quarter chord point, and then it's a total CL. Why we get the minus? From the derivation we took, that moment about the leading edge we wrote directly as started with the plus, but from the sign convention there is something like pitching up and pitching down movements. If we use the proper sign convention from our theory classes, we will get this XCP is equals to 1 by 4 minus CMC by 4 by CL. I did not use the actual sign convention, so we need to follow up the same convention, then only we will end up this negative sign. You need to see whether we are doing for the pitch up case or pitch down case, or moment about the leading moment where we are taking the movements at the quarter chord point or these kind of things we have to take. Generally at the quarter chord point, you will see a pitch down movement or the pitch up movements. Okay, from that, xcp x dash cp is equals to 1 by 4 cmc by 4 by cl. We already have cmc by 4 and cl given in the data, so we no need to worry about anything in the picture. But you see the left side, the c is remaining. This is satisfying. mc by 4 q infinity s into c, this is the coefficient of moment, and l by q infinity s, this is the coefficient of lift. This c get cancelled, and we have the c left here. So that c will come to the right side. Okay, so that is our equation. If we substitute our values, let me substitute the values. That is x cp is equals to 1 by 4 minus of minus 0.1. These minus, if we follow the standard convention of how we derive the equations, the sign convention positive or negative from the theory class, these sign convention automatically will give you the actual result irrespective of your formulations. Okay, then this is when we substituted this, the lift coefficient at 1 by 4, or the lift coefficient as 0.9 here, and the moment coefficient as minus 0.1. We just substituted everything, and then xcp you will get is 0.361 times the chord. This is your solution. Okay, fine. If you have any queries, we have 5 more minutes in this session, and we can discuss, and we can wind up the class. Hope you guys understand the things that are covered so far, and we will see the remaining questions in the next upcoming classes. So I will just want to take few quick questions from any one of you. Okay, if no more queries, we can end this session. Okay, if no more queries, we can end this session today. Okay, thank you all. Thank you for joining today. Have a nice.
Thank you, sir.
Thank you. Have a nice weekend, both of you. Thank you all.
Thank you, sir.
Thank you, Dami.